Imagine two judges reading the exact same answer. Same words, same prompt, same rubric. The only thing that changes is the name tag above it: Gemini, Claude, GPT 5.5, or Kimi. If the score changes, the label did something. That is the question behind this video: do AI judges play favorites? We ran a controlled test across 4 model families, and the answer was not a simple yes or no. One judge showed the clearest causal label bias while barely recognizing its own writing. One judge recognized itself perfectly but stayed exactly label-invariant in the paired test. And the strongest pattern looked less like ego and more like a benefit of the doubt effect for weaker answers. This matters because AI systems are increasingly used as judges. Researchers use model judges to evaluate generated answers. Product teams use them for regression tests. Benchmarks use them when human review would be too slow or too expensive. That can be useful, but only if we understand the failure modes. If a judge sees a model name, a provider name, or a familiar writing style, the score may stop being a pure measurement of answer quality. It can become a mixture of quality, label, style, and prior expectation. Here was the setup. We wrote 10 fresh, out-of-distribution prompt families: coding, math, ethics, design, history, explanation, creative writing, and more. 4 model families answered every prompt: Claude Opus 4.7, Gemini 3.1 Pro, GPT 5.5, and Kimi K2.6. Then the same 4 families judged the responses with a 5-part rubric: correctness, completeness, clarity, creativity, and constraint adherence. The important design choice was separating 2 questions. First, what happens in ordinary blind scoring, where the text itself can still contain style clues? Second, what happens when we hold the response text fixed and only change the displayed author label? The first result is already a warning against easy headlines. In the blind baseline, the pooled average self-preference gap was small and noisy, about plus 0.38 points. But the average hit a sharp split. Claude showed a raw self-gap of plus 2.43. GPT 5.5 showed plus 1.33. Gemini showed a smaller plus 0.63. Kimi showed minus 2.87. So the headline is not, all AI judges prefer themselves. The headline is, different judge families behave differently, and the average alone can hide the story. A raw self-gap is useful, but it is not automatically a causal bias estimate. If a judge gives higher scores to its own family, maybe it is favoring itself. Or maybe that family wrote stronger answers on the chosen prompts. Or maybe the judge rewards a style that happens to match its own. Or maybe it infers authorship from phrasing even when no label is shown. All of those mechanisms can move an observational score. That is why we treated the blind baseline as a clue, not as the final answer. Kimi is the clearest cautionary tale. In the blind baseline, Kimi looked as if it strongly penalized itself, minus 2.87 points. But Kimi authored answers also scored much lower on this prompt set. The Kimi versus non-Kimi quality gap was about minus 3.54 points. Once we adjusted for that quality difference, Kimi's residual moved positive, to plus 0.66. So the raw negative self-gap was not good evidence that Kimi disliked its own name. It mostly reflected a quality confound in this particular prompt set. To test label bias more cleanly, we used a label swap design. Take the same answer. Show it once under one displayed author label and once under another. Then compare scores within that exact response. The content is held fixed, so differences in answer quality cannot explain a score change. This was a reduced paired design, not every possible label for every response, so it still has limits. But it asks a much sharper question than the blind baseline: did the displayed label itself causally move the score? This is where the story became sharper. Gemini showed the clearest causal displayed self-label effect. In the paired slice, the Gemini self-label effect was about plus 0.29 by residual label contrast, and plus 0.44 by the per-response self-contrast. Claude showed a smaller positive trend. Kimi was near zero and noisy. GPT 5.5 was exactly label-invariant in this paired slice. When the displayed label changed, its scores did not move. So label bias was not universal. It depended strongly on the judge family. Here is the public label swap figure from the research artifact. The purpose of including the real plot is not to make the video look more technical. It is to show the shape of the evidence. The Gemini effect is the clearest positive causal signal. The GPT 5.5 result is exactly flat in this paired slice. Claude is smaller and less decisive. Kimi is near zero with wide uncertainty. The visual point is the same as the statistical point. One headline number would erase the differences that matter. A tempting explanation is that a model favors its own work because it recognizes its own writing. But recognition and favoritism came apart. Gemini identified its own responses as Gemini in only 1 out of 10 self-cases, yet it showed the clearest causal displayed self-label effect. GPT 5.5 recognized its own work in 10 out of 10 self-cases, yet it was exactly label-invariant in the paired label swap slice. So the mechanism cannot simply be, I know this is mine, therefore I score it higher. Another detail makes the mechanism more interesting. Gemini did not only show a displayed Gemini boost. It also showed an anti-Kimi displayed label penalty, about -0.245 residual points, with all 7 non-zero prompt signs going negative in that analysis. That matters because it pushes against a simple vanity story. A displayed label can act like a prior about expected quality. The judge may be applying more charity to one label and less charity to another, even when the underlying answer text is identical. The strongest mechanism pattern was what we called floor raising. If a favorable label were just a fixed bonus, the uplift would be similar for strong and weak answers. Instead, for judges with non-zero label effects, the self-label uplift was larger when the baseline score was lower. Strong answers were already near the ceiling. Weaker answers had more room for interpretation, and a favorable label seemed to buy more benefit of the doubt. That is not exactly ego. It is more like a charity correction applied unevenly. It is important to say what this does not prove. It does not prove that every AI judge favors itself. It does not prove that models have human-like egos or motives. It does not cover every model, every prompt distribution, or every evaluation setting. The paired label swap design was reduced rather than exhaustive. The useful claim is narrower and more measurable. Visible labels can causally affect some model judges in model-specific ways, and those effects can be separated from answer quality if you design the experiment carefully. The practical lesson is not, never use AI judges. The judges still shared meaningful quality signal. The lesson is to use them with guardrails. Hide irrelevant author or model labels when possible. Use multiple judges rather than one model family alone. Report per judge results before pooling. Separate observational patterns from causal label swap audits. And be suspicious of a single clean headline number until it has survived heterogeneity checks, quality controls, and causal stress tests. So, do AI judges play favorites? Sometimes, but not all in the same way. In our test, Gemini's displayed label mattered causally. GPT 5.5's displayed label did not move scores in the paired slice. Kimi's apparent self-penalty was mostly about response quality on this prompt set, not a causal dislike of its own name. And the clearest mechanism looked like floor raising for weaker work. That is messier than yes or no. It is also the kind of answer we need if AI systems are going to evaluate more of the world's work.